Okay, so let's try once again. Little clap. So I hope you see my book and you hear me well now. So yeah, I wanted to go back to the 23.4 example with that quantum state. It's omega, right? And example, so we talked about the rotational invariance here, and that because spin is rotationally invariant, we can choose any direction in space, and using different bases, we will have the same probabilities for different directions basically here. And Penrose afterwards goes into the example where he talks about like something like agreements and disagreements, like yes, 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 no, no, yes, and no, no results for two guys with detectors basically. And experimental Stapp looks like that. So we have like spin zero state here. It kind of disintegrates into two particles with opposite spins, 1/2 each, and one flies to the left, one flies to the right. This guy can measure the left particle using the up or right bases, and this one uses using the two bases which are oriented like 45 and minus 45 degrees from the vertical line here. Yeah, and then Penrose just states that the probability for those two to agree is this one, like 1/2 of 1 minus cosine theta, where theta is angle between the two chosen bases. So for example, if this guy chooses like vertical one and this guy this basis vector, and they will try to measure along those axes, then we will have like 45-degree angle between them, and the corresponding probability will be near like 15% here. So my question on the previous call was about that scene and like why probabilities are like that. And I prepared like a small notes here about this. So basically, to have an agreement, we have like two probabilities. Probability of having like yes at first detector and yes at two detector. That would be like the first type of the agreement. And the other type of agreement is two no's, like N1 and N2 here. And afterwards, I just kind of think about that as conditional probability, like what is the probability of having yes at the first detector if on the second one we get yes. And I just kind of decompose this probability on the left as the product of probability of yes happening at the second detector, which is 1/2, and conditional probability of yes happening at the first detector if yes happened at the second already. Actually, this situation is symmetrical, so it doesn't matter if you take like p y2 y1 multiplied by p y1 here. So the situation is totally symmetrical. And in this case, what we will have? So we will have that this probability here is 1/2, and this probability is actually equals to the N2 state multiplied by Y1 state. Because if on the second detector we got yes, then we know that particle which goes to the first detector will guaranteed to be in the N2 state. So we just projecting N2 state on the Y1 state and getting like modulus squared here, and that's exactly the our like cosine, but we need to have like 180 degrees here minus theta. So if you take a look at the angle between y1 and y2 here, then the angle between y1 and n2 will be like pi minus theta. So that's exactly what is written here, and therefore you can kind of think about that cosine in terms of the circle which I drawn here, and therefore you can replace this pi minus theta as minus cosine theta. So the final result you will get here is like 1/4 of 1 minus cosine theta. And actually the same thing will happen with the agreement for two no's here. So you will have 1/4 producted by the 1 minus cosine theta here. And at the end, the probability of agreement will be just the sum of those two possible cases, and you will have the formula which Penrose uses in the book. This 1/2 of 1 minus cosine theta, or sinus squared of theta over 2. And in the same way, exactly same way, you can obtain the probability of the disagreement here. Yeah, maybe you have some questions about this example?
I was thinking about, because you talked about the detectors.
Mm-hmm.
But how do you define what kind of things are detected in these cases? Is it specified anyway, or is it basically anything? So it's a yes and a yes or no in detector 1 and yes or no in detector 2. So what is detected there?
So I'm thinking about that in this way. So this particle and this particle could be represented as two spheres, basically. And the direction they are spin over could be described as any direction in the space. So I put like a small vector here. And we can think about those as lying in the one plane, actually. Just for simplicity. So we can just consider, instead of spheres, we can consider circles here, because like we can orient everything nicely, basically to be in the like one plane here. And if those two particles will, sorry, need to change, like will start their like flight here, then if you have like this direction here, you will have the opposite direction here, just from the like conservation standpoint. So basically what I'm thinking is that this particle is spinning over that axis. So its spin represented over that space direction in that circle. And in this particle, its spin is represented by this direction in this circle, like the opposite one. And here we have some kind of detectors like Stern-Gerlach or something, which can detect over like which axis in a space our particle is spinning. So
okay, it's about spins there.
Yeah, so we are measuring spin. We measure in spin, and we orient our like detectors here respectively. So respectively. So it could be, I think it could be spin and like magnetic moment and Stern-Gerlach detectors, or it could be some kind of polarizers, or like photo detectors and photons and polarized photons. But like photons have different spin, right? Not 1/2. So yeah, probably we should think about something else here. Yeah.
I think he maybe mentioned something about using polarization, but he said that it was not important. It would work for other things as well.
Yeah, it's just hard for me to say about like the real stuff going on here. So all I know is that we have like 1/2 spin particle and 1/2 spin particle here, and we will measure its spin over different axes here. And instead of using the sphere, we are using circles, because we kind of can orient everything nicely and assume that detectors and particles and their spins are just lie in like one plane. That's the way I'm thinking about that.
Could it be generalized so that you could just ask if something is happening, whatever it is, if something is happening in the detector or not, or if there is some property by some atom or electron or any particle or not?
Maybe, like it depends, because like that situation is exactly about like yes or no properties. That's just like how the quantum measurement works. Like you have like your yes or no answer basically.
But aren't we forcing yes or no answers from something that is more ambiguous probability-wise to begin with?
Not sure that I'm getting your point.
I'm saying that it isn't yes or no to begin with, but we are forcing it to become something.
Yes, good point. Is that one way to put it? Because there are so many possibilities to have the axis of the spin can be in so many directions.
Yeah, those axes could be in any direction, in any 3D direction you choose, or basically that thing at the moment of the collapse or like disintegration will choose. So, but here you will have the fixed thing, right? And the probabilities will be determined by the angles between that direction and the direction you chosen on the detector. So I'm not sure about generalizing to other detectors, but you just should think about that in terms of spin and in terms of like just having particle approaching with spin over some fixed direction in space, and detector has another direction in space. And there is an angle between those two directions, and we will have like yes probability with one with one value, with like depending on that angle we will have different probabilities basically, like when we project one direction over another, right? So, and that's basically it.
But the weird thing coming up is that these angles don't add up quite as expected, right? Or the probabilities don't add up as expected.
What probabilities haven't add up?
I don't think we have come to this point in the book yet, so let's wait.
But I just want to understand what you're talking about here. Like what exactly? Because currently in my head everything like is adding up nicely.
I'm talking about what is it? The 50% things that when you add them up, you expect 45% probability, but instead you get 85%.
You're talking about that thing, like classical versus quantum contradictions, and that thing. Yeah.
Yeah.
Yeah. Yeah. We'll talk about that later. That doesn't matter here. So, what I wanted to concentrate here is just that small example of like calculating agreement probabilities as joint one. And I was waiting for a nice question from you. And the question is why I haven't add those two probabilities here. Why I do not consider as those two events happening together. Because like the total probability law probably should we should consider like two cases, right? When we will have yes on the second detector, either or we will have yes at the first detector. I mean, we should sum up the probabilities here. But for some reason, I haven't done that. So the question is why? And actually that scene, so like initially I was going to do that, but I understood that I will have like doubled probabilities at the end here. And what this situation actually means if you look at the experimental setup, basically that means that we can kind of have some kind of like simultaneous measurements done. And I think that we shouldn't add those two things because they couldn't happen like both, because we kind of could have only particle measured initially at one detector and afterwards at the another one. So basically I can reformulate it as a simultaneity equation. So there is no simultaneity here in quantum mechanics. So we cannot simultaneously measure both particles at both detectors. There always will be the time discrepancy actually. And I read about that a little bit, and people explain that in terms of like uncertainty principle. That because of that you cannot kind of make the two systems measure two particles simultaneously, and so it's kind of like that. And basically in quantum mechanics also you cannot have like two simultaneous measurements done, and that's why you kind of can operate on such states like a Bell state here, because probably if you will measure it simultaneously, you will have just 1/2 and 1/2 probabilities on the both sides, and like particles will probably not kind of pass the impact of the one detector to the another one. Basically, like quantum correlation will not pass to the other particle. Yeah. So. And anyway, I think that's a really interesting question to think of later about the simultaneity of the measurements done in that really simple setup. Yeah, but anyway, let's take a look at those probabilities one more time. So what Penrose says here is that we will have like 4 different combinations of the detector to be chosen. Like we have 2 directions here and 2 directions here, 4 combinations in total. And we'll have 3 probabilities which are equal to 15%, and 1 probability which equals 85%. And afterwards he talks about like separating those detectors nicely between like Titan and other like really separated in a space object. And he says, suppose I have chosen like vertical direction and my colleague chosen 45-degree positive direction. Then after calculating the flow of the particles for, I don't know, some period of time, in a year or so when we will get back, we will see that our statistics has agreement near like 15%. The same way the probability theory here predicts. And if at the last moment he or his colleague will change the measurement directions to the other 45 degrees combinations, the probability will be the same, like 15% of agreement, and statistics will confirm that. And here we are supposing that like particles have no prior knowledge about how we are going to orient our measuring devices, right? So it should make no difference if we kind of suddenly changed our minds. And now we know that quantum mechanics predicts that the configuration when our two directions will have 135-degree angle between those. We should have like 85-degree percent probability of agreement. So, and the question here now is that consistent with the pairs of particles providing the correct joint probabilities for each of the configurations. And the key thing here is those four states Penrose introduces here at the bottom. Because he says if a particular particle pair is going to give agreement in the case of 135 degrees, then it cannot be in disagreement in all of the cases, in all of the other cases, basically, in all of the 45-degree cases. So what he wants to say here is that probability of agreement in the 135 case, this one, so of agreement, like agree, and that case here, right, equals basically sum of probabilities for each of those cases. So he kind of uses like simplified formula, so the actual formula is a little bit like fuller, or like you need to kind of subtract some other stuff from it. So basically you should have like inequality here. So that probability should be less or equal to the sum of the probabilities of having those three scenarios. So basically I will just name those like Pi and I, like from 1 to 3. Yeah, and you can check it by using something like that. So what I have here is actually I will try to explain at first this scene here. Sorry if that's not like really nicely drawn, but anyway, you can see that here I have like 135-degree case, and if you write down every configuration Penrose included in the book, you will see that each configuration is linked with next one by the like different detector states. So like agreement here is connected with disagreement here, or basically without those things, you just need to think about arrows here. So you can see that they are linked. This scene is linked to the second state by the first argument, and this second configuration is linked to the third by the second argument, and this in the same way the third configuration is linked to the fourth by the first argument. And now we kind of close up the loop, and we are connecting the fourth configuration to the first configuration by the second argument. So it's kind of circular configuration loop actually. And now you can add here agreement, disagreement things. So I just put those here and ask myself, like, why is it true? So why, if we have agreement in that case, if particles are not connected, we couldn't have the disagreements in all of those cases? So basically I wrote like the tree of possibilities here, right? So if we have the configuration of 135 degrees here and we have agreement, then either we will have two nulls, and then the particle states like measured will be like that, or we will have two yeses and particle states will just repeat the configuration for the measurement. And for yes, you can think later in the same terms I've been thinking here about two nulls. So for example, let's assume that we have a disagreement in the first case here in that second configuration. Then if we will have the disagreement, we can have two cases. One case is when we have like right and here we have like opposite direction, this arrow, or we will have left and the same arrow as here. So you can see now that in this case, we will have like a contradicting measurement done at the first detector. So you have right direction, meanwhile particle is known to be in the left direction. Therefore, that subtree isn't actually possible. So you can kind of cut out and just remove that part of the tree. So you just can not think about that. And if you'll go further and take, for example, like that third configuration is like vertical and 45 degrees from it. You will have this state, you will have two probabilities, two probable configurations of disagreement here. One is at the first detector we get yes, so top direction, and in the second detector we have no, so it's the opposite direction to that 45-degree direction. And you can see that in that case we will have one more time the conflict, but now in the second state of the particle. So we will have non-possible measurement done here, and therefore we can just cross out that possibility, and we are sure that to have the disagreement with the third configuration, the particle kind of should be possible to be measured like in this configuration, like bottom and 45 degree here. And currently those 2-3 measurements are kind of all possible for the actual particle. And if you come to the last one, thin, then you will have like conflict the same way we had in the two previous cases with the first state, but also you will notice that you will have also the conflict with the last fourth state here, but now with that first state we started here. So that state will conflict with this one because we'll have like top here, and that case will conflict with the first one because we'll have opposite arrow at the second detector. And therefore, because of that looped structure here of the configurations, that configuration of agreements and disagreements, basically correlations, they are conflicting. So basically, by just drawing the possible measurements, agreement, disagreement, like tree here, you can just kind of see for yourself that that you will have like a disagreement or basically like contradiction in that case. Yeah, and that's exactly what Penrose wanted to like us to show for us, that we cannot have that, and therefore we should have an agreement at least like one case here, either this, or either this, and therefore he kind of thinks about the agreement in 135 degree case as like probability of like 3 basically like events, like either it's agreement in first case, like agreement in first case, or don't like that. So like agreement in first case, or agreement in second case, or agreement in third case, something like that. So, and he just adds the 3 probabilities here. He earns or gets his 45% here, and he gets that this should be like greater than probability of having agreement at the fourth case, but that agreement is like 85%, and that's like the contradiction at the 23.4. Yeah, and actually these things, they are kind of not probably not really nicely presented either in the book, neither on my paper here. So actually there are some like even better examples. Probably I will show one more to you in a few minutes. Yeah, I just wanted to say that those agreements and disagreements are actually the things which are called like quantum correlations. So basically in probability theory, if you have like two random variables like xc1 and xc2, for example, and to say that they are non-correlated, there is no correlation between those, you can take like the expected or like expectation value of those, multiply those, and if those two random values are not connected, then expectation value of the product will be just the product of expectations. So if you expect on average one variable to give like result 2 and another to give result 4, then the expectation of the product, if there is no correlation, will be just 2 by 4 equals 8. Yeah, and I think that's why we can kind of associate the correlations with those like kind of products there, and that's why physicists are looking at those agreements and disagreements things here.
Slava, excuse me.
Yeah.
Can you say any example what kind of correlation we are talking about? Is it some events happening in time? Or?
Yeah, so we are talking about two correlations. Correlations of measurements done at two detectors. So we have two detectors. We have two possible and random values. The value xc1 here is basically you have experimentator here, and he kind of flip a coin. He flips a coin and have his direction for measurement chosen. So you have like a stream of the random variables called xc1 here, and stream of the random variables here, xc2. And probability of having that direction and that direction here is kind of 1/2 for both directions. So you just choose the direction by flip of the coin. So we have like two like random variables here. First of all, to choose the to choose the directions. That's the one random thing here. And the other random thing is the actually measurement done over that direction. So for example, I can call it like Z2, for example, and Z2 will be like a result of the measurement done at the detector 2. And those agreements and disagreements are actually products of those Z. So if you have Z1 here and Z2 here, then you kind of like the overall situation probably should be described in terms of xc and z also. So you should have like z1 equals yes and z2 equals also yes, and like for any xc1 and xc2 basically there. So the probability of agreement is something like that. And those things, those probabilities are actually connected with expectations. So because expectations of like z1 multiplied by z2, if you like say you can think about yes as 1 and about no as 0. So you will have something like different values for z1 and z2 here, and some probabilities of z1 and z2 having different yes or no results, like probability of z1 equals like a and z2 equals b, and you should have like a big sum here over the all different a and b's for different probabilities, and you will have your expectation value here. So for example, if you have a coin, you can have either like heads or tails, and you can say that heads equals 1 and tails like equals -1, then the total expectation value of like coin will be heads with 1/2, -1, 1/2, and it equals 0 in these terminologies. And I was talking here about like expectation of some Xi1, where Xi1 is the flip of the coin.
Okay, so this also resembles something like a coincidence. Coincidence is that basically if everything is random, you get as many yes, no, yes, and no cases. But if there's a relation and causality between the events, it's something else than the 25, 25, 25.
So
25.
basically, below those expectations, depending on the distribution of the random variables, there will be some kind of summation or integral. So you if you take a look at the Bell paper, and like maybe I can just open it on my other phone. Give me a few seconds, I just wanted to show you like Bell's case. For example, Bell's theorem, maybe that will suffice. One moment, I will switch to English because it's currently shown in Ukrainian. Yeah, so you can see here's the exact thing I was talking about. So basically the thing which is called correlation here is the expected or like expectation value of the product of two random variables, like depending on some hidden set of lambdas here, and so something like that. And you have like different distribution, like that p over lambda here, and that those p over p which depends on lambda here is just like probability distribution for those A and B things here. It's like joint distribution basically, because they are both kind of connected on the same lambda here. And you have like that sum, you have two values to be expected with some probability, joint probability p lambda here, and you can measure that expected value as that big summation here. So that's exactly what is happening in the like Bell's paper and Bell's theorem. So he using those expectations, correlations, and just kind of obtaining the Bell's inequality basically, which will contradict. So he will have something like this, and it could be shown that in quantum mechanics it contradicts to it basically. That but anyway, we shouldn't go there currently. I wanted to show you another example here, and this example is it's also called CHSH game. It is really connected with the example from the 23.4, and that's the reason I wanted to show it for you today. So actually that abbreviation is the surnames of 4 people, and they kind of make the improved from the experiment point of view Bell inequality. So there is this thing called CHSH inequality something, and the the advantages of their approach is that in experiment, while doing the Bell's theorem test in practice, you do not need to have two exactly oppositely polarized or correlated things. I don't remember exactly the exact scene, but actually all you should know here is that CHSH inequality was developed to make experiments happen, basically, or something. So let's take a look at this simple thing called CHSH game. So what we have here are just Alice and Bob, and Alice and Bob has two inputs called X and Y. They are random, so you can consider those as coin flips. And those two inputs are 0 and 1. So head or tails, right? We can say that heads are 0 and tails are 1s. So just two random and uniform distributed in terms of probability random inputs. So those inputs actually will kind of determine their choice of the basis to measure the particle in those two situations. So Alice is sitting here, Bob is sitting here, they're flipping a coin, and they are chosen in one of those directions with the same probability. And now they also have two outputs. And two outputs, they are kind of like two measurement results, A and B here. So they will either get yes or no. But currently we are just talking about the classical game. So they just have a coins and they could kind of flip it and afterwards take a piece of paper and write on a paper 0 or no. And the game is has the next rules, basically, that if the inputs are the same and they equal to 1, then to win they should produce different outputs. Like A shouldn't be equal to B. And in all other cases they should output the same numbers. And now the question for you, how do you think they what is the optimal strategy, classical one here, for those two guys to follow? Anyone?
Sorry, I lost my track. Why there are X, Y, and then A and B cases?
Yeah, so X and Y are inputs. So, and those inputs, for example, you have a coin. So I play with you, for example, right? And you have a coin and I have a coin. I can just flip it and have 0 or 1. Those are our random inputs. Okay?
Okay.
And the rules of game is if our inputs are the same and we both have sorry, one moment, because battery on my phone,
Power.
yeah, low on power. One moment. Yeah, so let's continue. So, for example, I and you, Mesocosmos, we have a coins, and we flip those. We will obtain some random things which we can call X and Y. So I will have X, for example, and I will get 0, and you will have Y, and you will have 1. So in that case, we should produce with you the same outputs. So I should say or write on the paper and show to you 0, and you will show to me 1 together. And we will win if we will produce the same outputs. Okay? If we haven't had tails boss, for example.
if they are same or they are
Yeah, so
inputs are same and the outputs
yeah, so
different.
if we have we should produce the different output only if we have tails both. So if you and I will have tails, then we should produce different outputs. And in all other cases, we should produce the same outputs. So what is the optimal strategy? What do you think?
What do you mean the optimal strategy?
Like, what should we do together with you to win that game, to maximize the probability of winning?
Okay.
So what is our strategy together? What should we do? For example, let's think. For example, I will always produce 1 as the output. And then what should you do?
Yeah, I should pick something, but I don't realize what is the winning situation.
Okay. You can see that like we know that X and Y, they are just coins. So those 4 cases, right? Probably I need to write it on the paper. So we have like X, we have Y, and we have 4 cases like 0, 0, 0, 1, 1, 0, and 1, 1, right? And probability of having all of those, like P of X, Y, I will write it like that, okay? So that X equals 0 and Y equals 0 is 1 over 4. This one is also 1 over 4. So they all are equally distributed in terms of probability, right? Because we just flip in the coin.
Yeah.
So, and now what we have in the game is that we know that to win, we need to maximize our expectation value. And expectation value is actually of what's seen here. It is that like we should maximize like expectation value of X XOR Y So sorry, I just don't remember the exact like logical thing, but anyway, we have like 4 cases, right? Equally distributed in terms of probability here. And we know that if we will together with you just output the same number, we will win in 3 of the 4 cases. So we will have the probability of winning 3 divided by 4, 75%. And actually you will not be able to beat that classically. So classically is the best thing we can do together is just output the same number. Just agree that you will output 0 and then I will also output 0 if I want to win.
Yeah, we can do that. I was also thinking that we can do agreement, but when is it a win situation? You mean it's a win when we get more than 1 over 5?
Win is described by those equations like X equals Y equals 1 and outputs are different. A doesn't equal B. We will win in that situation.
Okay.
And if inputs are different or they are both 0, then we will win if our outputs are the same. And
okay. So those are the winning cases.
yeah, those are the winning cases.
Okay.
Yeah. So by our strategy is connected with the outputs, basically, and we can do it sequentially, actually, right? So I can flip a coin, write down my X value. You can flip down the coin, write down your Y value. And afterward, you will show your paper. And you will show like 0 as the output. Yeah, sequentially, it couldn't be done sequentially. Okay, that's not the correct way to do that. So you should write your number, and I should write my number. And afterwards, we should like show it together to check up. So
Okay.
because
So you got a 0 and I got 1
yeah, and
by chance.
and for example, if you see like 0 and 1, then we have different outputs, and therefore we hope that we both had tails to win in that case. Yeah, okay, so basically here the idea is that like in the best classical situation here, the probability is 75%. And if you will use entangled pair, the way we have seen in the 23.4 here, then the probability will be cosine squared p over 8, and it will be 0.85, so like 85%. So in the same way, we kind of beat up the classically optimal strategy here using the quantum entangled pair. And actually, that's the exactly same case described here, which was described in the 23.4, that basically Alice and Bob have an entangled pair here, two bases, and they have the same angle between those, like p over 8 here, but actually p over 8 in the like basis notation, we know that theta angle is divided by 2, so actually those are like p over 4 and 3p over 4, and the situation is exactly the same as we had in the book. Yeah, so you can prove actually that in that case you will maximize the probability when the theta here is like p over 8, and yeah. So I think that's probably the simplest case you could have with the entanglement. So
Can some other people online comment on also on this, because I have seen this on some video, and it was still quite complicated. But here I don't understand the output part. If the input part is it is random, how do we connect with the output? How does it relate here? We want to send the message together somewhere, or how does it work?
In the quantum case or classical case?
Well, either.
Okay, in classical case, you can connect it any way you want, but it will not help you because it is random, right?
I think I share a similar confusion here on the selection of A and B. So is it that I flip a coin and then I just get to choose B?
Yeah.
So
yeah.
I flip a coin and I get Y, and then I just get to choose B that would be associated with this value for Y.
You can try to associate, but actually that will not help you in any way. So actually you will do your choice depending on your strategy. And strategy could be like any strategy you wanted to have. In a classical case, like there is no actually big dependence between X and A and Y and B, because you cannot get any information from the like random thing. I think that's the case in the classical example.
But the thing that we get to choose, that decides whether we win or not is we get to choose A and B.
Yeah.
And so if we both choose A and B to be 0, and we're just flipping coins for X and Y, then at best we'll be in 75% agreement.
Yes, yes.
I see. So, and then how does this example make sense in the quantum case? Like, where's the entanglement or like the dependence on Y and in B sort of thing?
Yeah, let's take a look. So here they have like two bases, U basis and V basis. And actually that's the same thing they had here. So, sorry, a moment. So you have two bases to measure over and like, so
and you choose like vertical or horizontal.
Yeah, so let's take a look at the picture in the Penrose book. So here you have Alice, and Alice has two bases, that vertical one and the right one. And she flips a coin and chooses randomly the basis to be measured here to wait for the particle coming from the right here.
Okay, so that gives us X. She chooses either up or right, and that gives us X.
Yeah. So our X is just the choice of the direction here, and Y here is also choice of the direction, but at the second detector. Those are our inputs.
Okay, and then what is A and B?
Results of the measurement. Yes or no.
I see. So the connection to like the coin toss in this CHSH game is that, you know, we're trying to kind of concoct a hidden variable theory. Is that right, Slava?
And what does it mean, concoct?
Oh, just like, you know, cook it up ourselves. Like we're trying to maximize our score to learn something about the distribution of hidden variables.
Yeah, so
the confusing part to me is in the CHSH game, we get to choose A and B, but in the quantum case, A and B are just the outcome of measurements. So we're not like really given the opportunity to choose our outcome.
Yeah. But that's the mechanism with which we can hack the probabilities, right? So it doesn't matter if we will choose it like using our free will or using any kind of mechanism.
I see.
So you can use anything you will imagine to produce those A and B.
Yeah, I just recalled also this part that the A and B they are the measurements, and the X and Y they are in the hidden trying to tweak out the measurements some hidden way.
Yeah. So anyway, my advice for you is to go to the chapter 23 channel, and on the next week take a look at the videos where that game is explained. I've shared a file with links to the videos for you there.
Okay.
Yeah, maybe that will help because I also feel that I do not understand probably it like really deeply. But anyway, it seems that I kind of have a lot more intuition here than in the Penrose example, actually.
Where did you post the links? Where did you post the links?
Channel 23 chapter 23.
So I totally see how we get this classical probability, like, and it's because we're using or and not like exclusive or. So like there's only one case where x equals y equals 1.
Mm-hmm.
But there are two cases where x or y is 0. Actually, three cases, right? Because if we just do an or and not an exclusive or, x and y could be 0, and that counts as that second case here. So 3 out of our 4 possible cases are met with this second condition, x or y equals 0.
3 possible cases are connected with A and B are equal, not with x and y equals 0, right? Because x and y are the things which are inside of those cases, right? They are. So you have 4 cases, and here you have just like x or y equals 0, and x and y equals 0, like 3 cases.
Right. So that gives us our probability of getting, or that gives us our 75% probability.
Yeah.
But just, I think I'm confused as to where A and B come in here, because we're already at 75% when we're only just considering the cases for x and y.
Yeah. So A and B here is in this strategy those 2 players will go for. So, and the best strategy for them is just to agree and to show always the same number.
I think I get it. So Alice and Bob are actually the particles. And by choosing a strategy, that's like a distribution of hidden variables.
Yeah, it seems so. Yeah.
So in this case, our winning strategy of just, we're both going to pick 0 independent of x or y. We're both going to pick 0 always. Then we'll have a 75% chance of agreement, because A is always equal to B. And x or y will be 0 75% of the time.
Yeah, so we kind of just relying only on the outputs in that case.
So, okay, just to make sure I get this.
Oh,
So
inputs,
Alice and
sorry.
Bob are the particles in this case, and A and B is the hidden variable associated with each particle. And if the particles are following this hidden variable theory, then they will essentially be trying to maximize their chances of winning, like in this game.
Yeah, that sounds familiar.
Yeah, I think that you are right. But I'm not sure about the last part you have said. So, like, basically our inputs here are the bases, right? So the measurement device we will choose to measure the particle. Alice and Bob are particles. And A and B are the results they will give us after the measurement, right?
Yep.
And could you repeat, please, the last thing? So basically, our strategy of showing the results is the probability distribution for the different results for those particles. And the probability distributions are exactly the same which are connected with the hidden variable theory, right?
Yeah, exactly. So the really simple case would be that A equals B equals 0, independent of what bases you decide to measure. That's the simplest case, where we're just both going to pick 0 for A and B, and we don't care what x and y are.
Mm-hmm.
So that would say we always agree if one of the axes or both of the axes are vertical, say. I think I'm getting more of this example. So it's the 75% probability is really just about this x or y equals 0, right? That just, the 75% comes from like the possibilities for x or y being 0. If both of them are 0, or if x is 0, or if y is 0. That gives us our 3.
Mm-hmm.
And the sort of winning strategy is whether we agree or disagree. And so a quarter of the time we should be disagreeing, and 3/4 of the time we should be agreeing. To maximize our score.
Well, there I lost the track. But just one comment that perhaps it's not really about tossing the coins for X and Y. It's a Y. It's more like we are choosing those values together. Is this correct?
Well, I think the design of this EPR experiment in general is that we should be separated over a distance where we can't actually communicate to choose our axes.
Yeah.
But we can agree beforehand whether we're both going to have like A and B equals 0, A and B equals 1, or if they're going to be opposite values.
Exactly. Yes. Yeah, that's a strategy. Yeah. So we can pick one of the four or three winning strategies.
Yeah. So that's the like history in short. That EPR paradox was introduced in 1935. Then Bell made his inequality or theorem, and Closer, Horn, Shimony, Holt, CHSH in 4 years they made a simplification, and afterwards Aspect was was able to do his experiment.
So with the classical situation, with the agreement, you can get the 75% at maximum.
Mm-hmm.
But with quantum tests and situation, you can go over that if the hidden variable is existent.
Yeah, so like basically to use that practically, right? You can use the same setup we had in the book. So like two guys, they're really separated in a space, like light years away from each other. They has a source which emits two like Bell state correlated particles to them. And to check up if so basically they can just kind of observe a stream of those particles, calculate statistics, and afterwards in a few years come up together, check up their statistics and see if they have 85%, then you have some kind of weird correlation happening basically, or which will kind of beat the optimal classical strategy here.
Yeah, and it kind of means that Alice and both those particles, they can communicate with each other and decide what to show on experiment. Gives that kind of...
Yeah, it's kind of hard to think about those examples. I mean, because even in that simple case, the guy or like professor there in the course, he hasn't provided the like explicit connection between quantum and classical case. So we kind of speak in the last half an hour or so about that, like how to connect that game classically to the quantum case. Yeah, and I think that Joyce really on the track here about the probability distributions of the hidden variables and the strategies connection here. Yeah, so it seems something like that here.
Can you, Joe, explain, did you get how the quantum got 85%, how it comes up? Is it due to some experiment or?
But it comes up from the book actually. So in the book it's described. So you have those formulas, you have your angles, and you just should orient your detectors in 135 degrees, and you will have your 85% agreement if quantum mechanics is right.
I see.
Yeah, and then that's like so we had the cosine squared. So this is just like a trig identity to go from the 1/2 times 1 plus cosine theta to cos squared of theta over 2. That's just like a trig identity.
Mm-hmm. Yeah, so Mesocosmos, have you found my article with links?
Yes, I found them from there.
Yeah, great. Maybe I wasn't like explicit about those because they're hidden in the article. So you should click the article on the Telegraph, go into it, and you will see a list of the linked items there.
Yes, yeah, I can see. I will take a look at all of those. It's a very exciting
so
topic.
I propose to finish this call with the hardest EPR example and just like go through it really quickly, because like anyway it will be hard to go into the details there. So maybe for the next time. Okay, so hardest EPR example. So we have the same situation as in the previous subchapter. We have like two guys making those experiments, but now they have the same directions. And those directions are up or right. And now instead of having the spin 0 particle, we have a spin 1 particle. And initial state of it should be with the Majorana description left and that 45 degrees state here. But actually that state is not the 45 degrees because he says here that state should be like with a theta angle here, which equals cosine of which equals to the 3 over 5. So basically it is just some other angle here. Okay, so, and we have that spin 1 particle with that configuration. And what does it mean here? You can see that tensorially, you can think about that as like plus Bell state here. And basically, it just says that your like spin 1 particle spins like the way I think about it, that like we have a sphere, we have two directions for the Majorana description, and basically you can think about the like collapse of that particle into two particles of spin 1/2 as like one part of spin is going to the left and one part of the Majorana sphere is going to the right. So I'm thinking about this way. So you kind of have two directions in space, and either one direction will go to the left and this one will go to the right, or other way around. Joe, am I right here in my intuition?
I think so. You mean just like reading the state aloud? Like so. Yeah. So what we're having is like the first particle in a left state, and the second particle in like a 45-degree state, and then what you have is switching them. So now the first particle would be in a 45-degree state, and the second particle would be in a left state.
Yeah, I just was thinking about like if you will think geometrically about like higher spin particles, you should recall that Majorana sphere, like from the chapter 22. And therefore I was just thinking about like two directions in space for the spin 1, and kind of one direction correspond for one spin 1/2 particle, and other direction corresponds for the other spin 1/2 particle. And when they separate, they kind of just split the sphere into two directions or something. So you obtain two smaller spheres, but now only with one direction.
Yeah, exactly. So when we combine so we get a Riemann sphere for one spin half particle, but in order to have the two spin half particle system, what we need to do is sort of like a, S2 cross S2 sort of thing.
Yeah. So anyway, you can change. You can not change. You can check. You can check that this state has the feature that it is not orthogonal to the down-down state, but it is orthogonal to each of those three states, like down, left, down, and right. I've tried that, and I still haven't managed to prove that. But anyway, you can believe this here, and from those properties, from those orthogonality things, you can deduce 4 more properties described here, like 0, 1, 2, and 3. So they are like every one of those 4 orthogonal relations are respectively responsible for those 4 properties. So non-orthogonality to the down-down state corresponds to the 0 properties, that sometimes I will obtain no for the up measurement, and my colleague will obtain no for the up measurement also. Sometimes. And orthogonality of that state means that something will never happen, or will happen definitely. So you can formulate that orthogonality to the down and left state means that if I obtain no for the up measurement, then my colleague must obtain yes for the right measurement. And that's actually connected to that opposite state, right? Because if I obtain no for that measurement, then I'm sure that I obtained the left. Then I'm sure that I have obtained the down state, and now my colleague, if he will measure in the right basis, then he must obtain right, because we cannot obtain left, because our original state is orthogonal to that tensored left state here. So left and down measurement is impossible for our system. And in the same way, left and down symmetrically is also impossible. And therefore we have a symmetrical statement that if my colleague obtains no for the up measurement, then I must obtain yes for the right measurement. So 1 and 2 are symmetrical things. And now for the last one, if we have like two right states here and orthogonality to those, then I will never obtain yes for the right measurement when my colleague obtains yes for the right measurement also. Yeah, so that's the setup, and you can see the similar setup of the experiment here. Instead, we have like spin one particle here with two Majorana directions here. Okay, yeah, and he says that we can actually calculate the probability to perform the up measurement for both guys here, and it's exactly 1/12. Okay, and it's kind of really close to the optimal value Hardy used in his paper. Yeah, and now Penrose just finishes with like why this case isn't possible. And argument is kind of really similar to the scene we had previously in this disagreement case and like loop connected configurations here. So instead of configurations, we have like those four properties. And now he just says that like if two particles are separate, non-communicating entities without foreknowledge of the experiments to be performed upon them, we will have like contradictions because in the case of zero, the two particles must each be prepared jointly to provide no answer from time to time. And to the eventuality that both I and my colleague might simultaneously perform, okay, so if they perform like two up measurements there. And yeah, yeah, and also like those guys can change their mind and measure like one guy will measure in the top basis, another guy will measure in the right basis. And particles must be prepared somehow to give definitely the yes answer on those occasions for the right measurement, if just one of us will switch to that basis. To like not to violate one or two properties. Yet the very decision, that decision will kind of make a contradiction with the third property, because I and my colleague might both happen to perform right measurements on some occasion and thereby obtain the forbidden result yes, yes. Because like, so basically he just says that like properties 1 and 2 will give us the like pre-programmed thing to return yes for the right measurement definitely. But if those two experimenters will decide to measure together with the right bases, and particles are like formed were prepared independently to return you the yes for the right measurement, he says that like the theory says, or like that property says, that we should never obtain yes for the two right measurements. And classical theory says that there is a probability of having that. So yeah, I'm not sure that I understand everything here, of course. But anyway, I think I need to go into the details on the next call, and maybe to obtain the correct probabilities, and when I will have like the correct form for that state in terms of left-right basis and up-down bases, those properties will be more understandable. Okay. So
yeah, I think there's a lot of algebra, because like just to write a like a spin x state, or a spin state along x, it's some combination of the up and down states. And then also your diagonal state will be another combination of the up and down states, because it's like spin up plus spin right sort of thing. But spin right is already a combination of spin up and spin down. So it's going to be a big algebra task.
Yeah. So just to...
Do you mean that 1/12 is coming from this algebra, or?
Yeah, so what the 112 is basically the projection of the initial state onto, I think, the up state.
Actually,
but that initial state is some big combination of up and down. Yeah, okay.
It seems that here, but I don't remember, seems somewhere here. No, sorry, it seems another calculation. Okay, somewhere I already started doing that algebra thing, but I wasn't able to come down with the right results. Maybe I have some mistake there, so I need to reconsider it from the beginning. I also... Yeah.
Yeah, please, Joe.
The thing that would probably stump me a little bit is this 45-degree state. Is that just like spin up plus spin right? I don't know offhand. Because you'd think if you're just adding like these basis vectors, then it would just be spin up plus spin right. That would give you a 45-degree state.
So, sorry, it seems I lost you. Probably a bit tired already.
Oh, that's okay. I was just saying that the 45-degree state would be some combination of spin up and spin right.
You mean tensor combination or something, because you can choose only like so by this I mean that you have like two particles tensor here, right? And you can choose different bases for those, so you can choose like up here and right here. Do you mean this combination? Because
no, not necessarily. So I'm just talking about like the single particle state. If we go up to, actually it's on this page, so just on the line above where you're at now. Yeah, so where you have the Majorana state is symmetric. That equation is what I'm talking about. So see how the second particle is in the like 45-degree state? Just write a ket with like a single particle in the 45-degree state. Yeah, so just that ket.
Yeah. So you will just consider it to be like 1 over square root 2 of like up and down, something like that.
No, because that would be like a right state. That wouldn't be the 45-degree state.
Yeah, sorry. So you should consider different probabilities here, probably.
Yeah, so I think...
So you will have like, I don't know the exact numbers currently, but if you'll think about that, so it will have like cosine theta here is 3 over 5, right? 3 over 5.
Oh, okay.
And therefore it will be something like 1 minus 3, 5, 2, 5, and probably square root of 2 over 5, like up, or something like that. And I was just like assuming something like that, like similar to these numbers.
Yeah, and I think there's one more step to get there. Those do look like Clebsch-Gordon coefficients, but...
Yeah, actually, like today's call went as like really unplanned, in the unplanned direction. I wasn't planning such a long thinking about the examples, but it seems we need to think more.
Well, for me, it's at least it's easier to grasp these ideas by examples. Anyway, so it helps me.
That's great. So, yeah, and despite talking about everything today, I think we still need more time, and I have a proposal to work more on the examples. Like, let's for the next time think more about the example in 23.4, hardest example, and CHSH game. Okay?
Yeah, sounds good.
Let's research those 3 cases and like squeeze the maximum from those, like juice them out. And in this case, we will have like more time for guys to catch up, also to read the same things, right? So let's just pause chapter 23 at 23.6 here. And let's talk about practical examples before we will go to the more theory and discussions, okay?
Yeah, sounds good.
So what was the other example? It's 5, the video 5 on the list, and it's the CHSH.
Yeah, so we have one example in 23.4. The example where we have 45% probability, which is less than 85% probability. And I'm not sure I understand that exactly. Like, why is it happening? Why he like got those summation of like 3 cases. So I'm not kind of sure about his arguments here about having contradiction here. So I know if if you take a look at the tree of possibilities here, yeah, we will have a contradiction, but like I'm not sure why can we sum up all of those probabilities. So I'm still not really clear about those. I kind of believe it, that it seems like so like that is the right thing to do, but I'm not kind of sure about that. So maybe anyone can add something to that example next time. Yeah, and also we have CHSH game example, and here you can watch the videos I've sent to you, and we can try and build the explicit connection between the classical CHSH game and quantum one. All right, and then we will understand it much better. And I think understanding this one will give us better understanding of that one. So basically we can just have like a skeleton of the CHSH game. We can put on that skeleton the first example, and we will understand more about the first example and the correlations and stuff like that. Yeah, and the last example is the hardest example with spin 1 particle. So 3 examples for the next time.